Somewhere beyond the edge of everything we have ever mapped, beyond the last planet, beyond the last whisper of the sun's magnetic breath, a machine the size of a small car, built with 1970s technology, running on less electricity than a refrigerator light bulb, suddenly went silent. No warning. No error message broadcast to the world. Just silence. For days, the most distant human-made object in the history of civilization stopped talking to us, and the engineers at NASA's Jet Propulsion Laboratory, the people who had spent decades keeping this machine alive across 15 billion miles of darkness, sat in front of their screens and heard nothing. Think about what that silence actually means. Not a satellite blinking out over a city, not a phone call dropping, a spacecraft we launched in 1977 which has traveled so far that a radio signal moving at the speed of light takes over 23 hours just to reach it. That machine went dark. And when it finally came back, it wasn't speaking the same language anymore. What you're about to hear is not a story about malfunction. It is not a story about failure. It is a story about what happens when human beings refuse to let go of the most extraordinary thing they have ever created, even as it dies by fractions in the cold between the stars. It is a story about desperation disguised as engineering, about 46-year-old code being rewritten from 15 billion miles away, about a transmitter that hadn't been used since 1981, waking up in the outer darkness and whispering back to Earth. And it is a story about a countdown that is already running. A countdown that, when it reaches 0, will end the only direct conversation humanity has ever had with interstellar space. Voyager 1 is a space probe launched by NASA on September 5th, 1977. Most people know that. What most people do not fully understand is what that number means in practice. 1977, that is the year of the original Star Wars. That is 4 years before the IBM personal computer existed. The engineers who designed Voyager 1 did their calculations by hand and on early mainframes. The software coded into its computers was written for a 5-year mission, a planetary flyby of Jupiter and Saturn, and then a graceful retirement into silence. Nobody seriously planned for what came after. Nobody drew the blueprints for keeping a spacecraft operational for nearly half a century because nobody believed it would survive that long. But it did. It kept going. And now, in 2026, almost 50 years later, the people at JPL are fighting every single day to keep it alive, making decisions with consequences that arrive almost 2 days later, managing a machine so old and so fragile that turning on a single heater can trigger a cascade of autonomous emergency responses that nearly kills the mission entirely. Voyager 1 began transmitting unreadable data on November 14th, 2023. That was the first major alarm. For months before anyone made a public announcement, the engineers noticed something wrong in the signal. The data coming back was not corrupted in the way hardware damage looks. It was not fragmented or noisy. It was structured. It had the right shape, the right rhythm, the right timing. But it was completely meaningless. Voyager 1's binary code, the computer language it uses to communicate with Earth, stopped making sense. Its zeros and ones didn't mean anything anymore. The engineering team described it in terms that still feel unsettling. The call between the spacecraft and the Earth was still connected, but Voyager's voice had been replaced with a monotonous dial tone. The spacecraft was talking. It just wasn't saying anything. And here is where the situation gets genuinely strange. This was not a transmission problem. The signal was traveling correctly. The Deep Space Network antennas were receiving it perfectly. The glitch was found in NASA's Flight Data Subsystem, or FDS, the system responsible for packaging the probe's science and engineering data before the radio transmitter sends it back to mission control. Something inside that system had broken, something deep in the software architecture of a computer designed in the early 1970s, running on hardware that had been bombarded by cosmic radiation for over 4 decades, had simply stopped working correctly, and the team did not know what. They suspected, they theorized, but to confirm anything, they had to ask the spacecraft directly, and then wait nearly 2 days for an answer. On March 3rd, 2024, Voyager 1 operators sent the spacecraft a specific command intended to prompt the Flight Data Subsystem to send a full memory readout back to Earth. The readout confirmed to the NASA team that about 3% of the FDS memory had been corrupted, and that this was preventing the computer from carrying out its normal operations. 3%? That sounds almost trivial until you understand what it means on Voyager 1. The total memory on this spacecraft is 68 kilobytes. Not megabytes, not gigabytes, 68 kilobytes. Less storage than a single low-resolution photograph on a modern phone, and within that impossibly small memory, a chip had failed. JPL's chief engineer identified the failed component as a single RCA, CD4061A CMOS RAM chip, which held 256 words of FDS memory. Whether a cosmic ray particle had struck it at high speed or it had simply worn out after 46 years, nobody could determine. And it made no practical difference. The chip was gone, and the code that lived on it was gone with it. What happened next is one of the most extraordinary feats of software engineering in the history of space exploration, and most people have never heard about it. The Voyager team began developing a workaround. The code needed to be relocated, but there was no place for an extra 256 bits. Think about that constraint. There was no spare space anywhere on the spacecraft's computers. Every byte was occupied. So the engineers had to find a way to compress and redistribute the code, breaking it into segments small enough to fit into different available locations, scattered across the computer's memory, like hiding pieces of a puzzle in separate rooms when the original room burns down. But here is where it gets worse. They also had to delete something. To make room, the engineers deleted unused code. For example, the code used to transmit data from Jupiter, which could no longer be used at the current transmission rate. They were stripping the spacecraft of its past to save its future, and then they sent the fix across 15 billion miles of space and waited 45 hours to find out if it worked. On April 18, 2024, the team began sending the code to its new location in the FDS memory. By April 20th, the team confirmed their modification had worked. For the first time in 5 months, scientists were able to communicate with Voyager 1 and check its health. The people in that room at JPL had just debugged and patched a 46-year-old computer from 15 billion miles away by writing new code, transmitting it at the speed of light, and waiting a full day each direction to confirm the result. There is no analogy for what that feels like. There's no human experience that quite maps onto the tension of sending a message and knowing the reply will arrive tomorrow, and knowing that if the reply contains the wrong information, you might never get another chance. They pulled it off. The mission continued. But the story was far from over, because barely 5 months after that triumph, Voyager 1 went silent again. And this time, the nature of the silence was different. On October 16, 2024, the flight team sent a command to turn on one of the spacecraft's heaters. While Voyager 1 should have had ample power to operate the heater, the command triggered the fault protection system. The fault protection system is essentially Voyager's survival instinct, an autonomous set of responses designed to protect the spacecraft when something goes wrong, without waiting for instructions from Earth. If the power drops too low, if a system draws more than it should, the fault protection system acts. It shuts things down. It makes decisions on its own because there is no time to wait 23 hours for a human to respond. The team learned of this. The engineers searched. They knew the spacecraft must still be transmitting something because the fault protection system would not simply shut down all communications. They scanned the frequencies. Engineers correctly hypothesized that the fault protection system had lowered the rate at which data was being sent back from the transmitter, which changed the nature of the signal the deep space network needed to listen for. They found it. A whisper, not a voice. The same transmitter, the same frequency, but running so slowly and so faintly that it had effectively become invisible to the standard monitoring systems. They recalibrated. They located the signal. They breathed. And then, the next day, the signal vanished entirely. On October 19th, communication appeared to stop entirely. The flight team suspected that Voyager 1's fault protection system was triggered twice more, and that it turned off the X-band transmitter and switched to a second radio transmitter called the S-band. The X-band is Voyager's primary voice. The S-band is the backup, quieter, weaker, and operating on a different frequency. There was one enormous problem with this development. Voyager 1 had not used the S-band transmitter to communicate with Earth since 1981, not since Ronald Reagan was in his first year as president, not since the spacecraft was still inside the solar system, still relatively close to home. In 1981, the S-band was a reliable secondary channel. In 2024, with the spacecraft more than 15 billion miles away, nobody knew if the signal would even be detectable. The antenna arrays on Earth were not calibrated for it. The signal would be extraordinarily faint. For 3 days, the most distant object humanity had ever built was effectively invisible. A ghost ship in the dark, transmitting on a frequency we had not listened to in over 40 years. While Voyager 1's team wasn't sure that the faint S-band signal would be detectable due to the spacecraft's distance from Earth, Deep Space Network engineers located it. They found it. Against all reasonable expectation, the ancient transmitter was still working, its signal still coherent enough to be identified from 15 billion miles away by antennas that had to be manually tuned to find it. But finding the signal was not the same as restoring communications. A NASA spokesperson told reporters that if they couldn't turn the X-band transmitter back on, the Voyager 1 mission was effectively over. The S-band transmitter wasn't powerful enough to send telemetry, let alone science data. There would be no engineering data to assess the health of the spacecraft. The mission was hanging by the thinnest possible thread, a 43-year-old transmitter, whispering from the edge of the solar system, too faint to tell the engineers whether the spacecraft it was attached to was dying or not. The mission is working with extremely small power margins on both Voyager probes. Powered by heat from decaying plutonium that is converted into electricity, The spacecraft lose about 4 watts of power each year, 4 watts per year. That is the pace of death for Voyager 1. Not a catastrophic failure, not an explosion, not a collision, just a slow, relentless subtraction of warmth and energy as the plutonium inside its generators decays. For the first decades of the mission, 4 watts per year was manageable. Systems were shut down one by one, methodically, carefully. Cameras, sensors, heaters. Each sacrifice bought more time for the instruments that mattered most. About 5 years ago, some 41 years after the Voyager spacecraft launched, the team began turning off any remaining systems not critical to keeping the probes flying, including heaters for some of the science instruments. They were turning off heaters in a machine traveling through a region of space where temperatures approach absolute zero. They were gambling, carefully and deliberately, that the instruments would survive the cold, and those gambles were paying off until the day they tried to turn a heater back on to save a degrading circuit, and the spacecraft interpreted the power draw as an emergency and shut itself down. Earlier this year, the declining power supply required the team to turn off a science instrument on Voyager 2. The mission shut off multiple instruments on Voyager 1 in 1990 to conserve energy, but those instruments were no longer in use after the probe flew past Jupiter and Saturn. By the time of the October 2024 communications crisis, Voyager 1 was already stripped to essentials. The fault protection system that triggered the transmitter shutdown was not responding to genuine danger. It was responding to a power system with no slack left, no buffer, no room for an unexpected draw. The engineers had eliminated every non-essential system years ago, and now the fault protection software was looking at what remained and still finding it was not enough. Historically, if the fault protection system sensed that the probe had too little power available, it would automatically turn off systems not essential for keeping the spacecraft flying. But the probes have already turned off all non-essential systems except for the science instruments. So the fault protection system turned off the X-band transmitter and turned on the S-band transmitter, which uses less power. The spacecraft's own survival instinct had decided that the primary radio was a luxury it could not afford. NASA's Voyager 1 resumed regular operations following the communications pause. The team reactivated the X-band transmitter and then resumed collecting data the week of November 18th from the 4 operating science instruments. The crisis was resolved. The mission continued, but something had changed in how the people managing Voyager understood the situation they were in. This was not a problem that had been solved. This was a warning, a demonstration of how little margin remained, how close to the edge the mission was operating, and how a single routine command could cascade into a near-total communications blackout. The spacecraft was still alive, but it was alive the way a person in critical care is alive, functional, monitored, existing within a set of conditions that had to be maintained with extraordinary precision and a great deal of luck. And then the quiet losses began accelerating. On April 17, 2026, mission engineers at NASA's Jet Propulsion Laboratory sent commands to shut down an instrument aboard Voyager 1 called the Low Energy Charged Particles Experiment, or LECP. The LECP had been operating almost without interruption since launch in 1977, nearly 49 years. It measured ions, electrons, and cosmic rays from both inside and outside our solar system. It had been one of the instruments that confirmed definitively that Voyager 1 had crossed the heliopause, the boundary where the sun's influence ends and true interstellar space begins. Voyager 1 crossed the heliopause and entered interstellar space on August 25, 2012, making it the first spacecraft to do so. The LECP was one of the instruments that witnessed that crossing, that measured the change in particle environment as the probe moved from one regime of space to another. And now, 49 years after launch, and 14 years after that historic boundary crossing, engineers turned it off, not because it had failed, but because they could no longer afford the power it consumed. The decision came after a routine roll maneuver on February 27, 2026, revealed that Voyager 1's power levels had dropped unexpectedly. If the power levels dropped any lower, a decrease would trigger an autonomous failsafe called the Undervoltage Fault Protection System. The engineers described it in terms that make the stakes immediate. The Voyager mission manager at JPL, Kareem Badruddin, offered an analogy that is hard to forget. Fault protection is like a safety net for a trapeze artist. It is there if needed, but the trapeze artist should never let go of the trapeze, because once the fault protection system activates an undervoltage response, recovering the spacecraft from that state requires a lengthy, complicated, risky effort from the ground. And those recovery efforts take place across a communication gap that is now approaching 46 hours round trip. Every problem on Voyager 1 is a slow-motion emergency, solved in a time zone that no human psychology was designed to operate within. As of April 2026, only 2 Voyager 1 science instruments remain switched on, the magnetometer and the plasma wave subsystem. 2 instruments, out of the original 10, the spacecraft that once returned breathtaking images of Jupiter's storms, that photographed the volcanic chaos of Io, that captured the rings of Saturn in detail no telescope from Earth had ever matched. That spacecraft now has no cameras, no imaging equipment, no ability to show us anything. It listens. It feels. The magnetometer measures the magnetic fields threading through interstellar space. The plasma wave subsystem detects the behavior of the thin ionized gas through which the probe travels. Two instruments, both measuring things that are invisible to human senses, both operating in a region of space that no other functioning spacecraft in history has ever reached. Those final two instruments matter because interstellar space is not empty. The magnetometer measures the local magnetic field. The plasma wave subsystem can detect plasma oscillations and other radio frequency signatures that help scientists infer the density and behavior of ionized gas around the spacecraft. What most people are not seeing is the specific scientific value of what those two remaining instruments are doing right now, today, in July 2026. The interstellar medium, the space between star systems, is not the empty nothing that the phrase implies. It is a complex, structured environment filled with the remnants of dead stars, threaded with magnetic fields, filled with charged particles from supernovas that occurred millions of years ago. We have theoretical models of this environment. We have observations from Earth-based and space-based telescopes. But we have never had a spacecraft actually inside it, measuring it directly, until Voyager 1 and then Voyager 2. Those measurements are unique in a way that is almost impossible to overstate. There is no other source of this data. There is no instrument on Earth, no satellite in orbit, no telescope anywhere that can tell us what the plasma density of local interstellar space is right now, what the magnetic field strength is, how those values vary over time. Only two machines can do that, and they are both running out of power. Engineers hope the latest sacrifice can keep Voyager 1 operating long enough for the team to potentially roll out an upgrade, nicknamed the Big Bang, a coordinated swap of several powered components all at once, trading older systems for lower power alternatives. The name is both dramatic and accurate. It is not a gradual adjustment. It is a comprehensive, simultaneous restructuring of how power flows through the spacecraft, a kind of controlled electrical revolution enacted from a distance of 15 billion miles on hardware that has never been tested under current conditions because there is no way to replicate current conditions here on Earth. The team will implement the Big Bang on Voyager 2 first, which has a little more power to spare and is closer to Earth, making it the safer test subject. Tests are planned for May and June 2026. If they go, well, the team will attempt the same fix on Voyager 1 no sooner than July. And if it works, if the Big Bang successfully reorganizes the power architecture and buys back enough margin, there's even a possibility that the LECP could be switched back on, that a 49-year-old instrument just shut down to prevent catastrophe could be brought back to life. Everything on board is single string, according to Voyager project manager Suzanne Dodd. Single string. That means there is no redundancy, no backup, no plan B for any critical system. If the magnetometer fails, it is gone. If the plasma wave subsystem fails, it is gone. If the primary transmitter has another crisis like the one in October 2024, there's a real possibility that it cannot be recovered again. Every system on this spacecraft is the last of its kind on this spacecraft, operating without any fallback, billions of miles from any possibility of physical repair. Between May 2025 and February 2026, Deep Space Station 43 in Canberra, Australia, the only antenna capable of sending commands to Voyager 1 and 2, was offline for major upgrades, with only limited operational windows in August and December 2025. This created a critical deadline for engineers to revive backup roll thrusters before full loss of communication. Read that again. The only antenna on Earth capable of sending commands to Voyager 1 was offline for 9 months. During that period, engineers had only narrow windows, brief reopenings of that communication channel to execute critical operations. If something had gone wrong with the spacecraft during those months, during the long stretches when no commands could be sent, the mission might have ended silently without anyone being able to intervene. The mission is now operating within constraints so tight that the maintenance schedule of a single radio telescope in Australia becomes a critical variable in whether humanity's farthest probe survives another year. In November 2026, Voyager 1 will reach a distance of 1 light day from Earth, the first human-made object to reach that threshold. 1 light day. A radio signal traveling at 300,000 kilometers per second will take 24 hours to cross the distance between Earth and this machine. The milestone will pass quietly. No ceremony. It can match the scale of what it represents. A thing built by human hands, assembled in a factory in Southern California, launched on a rocket that burned for less than an hour, will be so far from the planet that spawned it that light itself needs a full day to make the crossing. And the two instruments still running on that machine will still be measuring, still sampling the interstellar medium, still sending data back that takes a full day to arrive. Think about what that means for the engineers who receive it. They are reading the present state of a spacecraft as it existed yesterday. They are managing something in real time that is, by definition, always in the past. The carrier signal itself will continue beyond the end of the science mission, unmodulated with no one able to listen meaningfully on the other end. What we keep returning to, in pieces like this, is how unusual the operational discipline around Voyager has become. At some point in the 2030s, if the spacecraft survives that long, the last instrument will go dark. The magnetometer, or the plasma wave subsystem, whichever holds out longer, will finally consume more power than the decaying plutonium can provide, and it will shut down. The radio transmitter may continue for a while after that, broadcasting a carrier signal with no science data attached, a heartbeat with no message, a voice with nothing left to say. And eventually, that too will fade. Not with a bang, not with a dramatic final transmission. Just a gradual weakening of the signal until the noise floor of the universe swallows it completely and Voyager 1 becomes, at last, truly silent. But here is what haunts this story. Here's the question that does not go away no matter how many technical details you understand, no matter how thoroughly you grasp the engineering realities. Voyager 1 is more than a spacecraft. It carries a golden record, a physical artifact, a disk of gold-plated copper containing sounds and images selected to represent the diversity of life and culture on Earth. Music. Greetings in 55 languages. The sounds of surf and wind and thunder and whales. Mathematical diagrams. Photographs of humans and animals and landscapes. A message to whoever or whatever might someday find it. That record is still on board. It is traveling through interstellar space right now, beyond the reach of the sun, on a trajectory that will eventually bring it close to other star systems. Not for thousands of years, not for tens of thousands of years, but eventually. The machine will be dead long before then. The plutonium will have fully decayed, the transmitters will be silent, but the golden record will still be there, intact, waiting. The engineers at JPL know they are managing the final years of Voyager 1's operational life. They know the instrument shutdowns will continue, that the Big Bang upgrade is a long shot, that every year from now until the 2030s is borrowed time. They also know they are the custodians of something irreplaceable. The only probe ever to send data from beyond the heliosphere, the only machine ever to make direct measurements of the local interstellar medium, the only human-made object to cross into the space between the stars and keep talking back to us. And they show up every day and do the math and send the commands and wait 46 hours for answers. Because the alternative is letting the mission die on their watch when there might still be something they can do. The Big Bang upgrade may work. It may buy another year, maybe two. The last two instruments may survive into the 2030s, returning data from a place no future spacecraft will visit for decades. NASA's proposed interstellar probe would see a slingshot mission out of the solar system, departing sometime in the mid-2030s. If that mission ever launches, it will be faster than Voyager. Will reach the heliopause in a fraction of the time and will carry modern instruments, but it will arrive at Voyager's current position in roughly the 2070s. And between now and then, between the death of Voyager 1 and the arrival of whatever comes next, there will be a gap. A period when no human instrument is measuring the interstellar medium, when the most extraordinary scientific vantage point ever achieved will be occupied by a silent, drifting, golden-plated ghost. What comes back when Voyager speaks now is not just data, it is a kind of testimony, evidence that something built by one generation of human beings can outlast every reasonable expectation, can survive on the edge of the possible for nearly half a century, can be repaired and extended and coaxed back to life by engineers who were not yet born when it launched. But testimony ends. The question that remains, the one nobody can answer yet, the one that is still being decided by power margins measured in fractions of a watt and thruster tests conducted across billion-mile distances and a software upgrade called the Big Bang, is simply this. How much longer? How many? More transmissions? How many more mornings will the deep space network antennas rise toward the sky and find, against all odds, that something is still out there, still talking, still alive? Nobody knows. And that uncertainty is not a problem to be solved. It is the sound of a story that is not yet over, reaching us from the farthest edge of everything we have ever touched.